Hello, welcome to ANS Solver. This is the second question of the paper. Now, the heights of a certain species of animal have been found with the mean of 65.2 centimeter. Okay, and a standard deviation of 7.1 centimeter. A researcher suspects that animals of this species in a certain region are shorter, that means lesser, on average than elsewhere. She takes a large random sample of N animals of the species from this region and finds their mean height to be 63.2. Now, if you see, you have your mean here, you have your standard deviation here, and this is basically your test value, correct? Because this is what, when you test, that's the value you get. She then, she then carries out an appropriate hypothesis test. She finds that the value of the Z statistic is minus 2.182, correct to 3 decimal places. Stating a necessary assumption, calculate the value of N. So first the assumption is that the standard deviation is same or constant at 7.1 centimeter. Okay, that's the assumption. Now, I need to calculate the value of N. I know one formula which states that the Z statistic value equals to the test value minus the mean over the population standard deviation over root N. We have the Z statistic value with us, which is minus 2.182, equals to the test value, which I know is 63.2, minus the mean, which is 65.2, over the standard deviation, which is 7.1, over root N. Got it? So now what I can simply do is, I can write this as minus 2.182 into 7.1 over root N equals to, I know 63.2, I can, okay, minus 65.2, which is the mean, okay, is simply minus 2. So now I can simply calculate this, minus 2.182 into 7.1, okay. This should be divided by negative 2 to give my root N basically as 7.7461. So I get my N basically as 7.7461 the whole square, with N basically as 60. You'll get 60.0002, but you can round it off to 60 because N needs to be a whole number. Got it? Now, carry out the hypothesis test at 4% significance level. So I can state my null hypothesis, which is my initial claim, which states that my mean is 65.2. So I can simply say my mean is equal to 65.2. Then I can say my alternative hypothesis, which is the claim that I will claim, which states that this has become shorter. The mean is shorter. That means the mean has decreased from 65.2. Now what do? I know I have a 4% significance level, which is basically something like this. Because this is less than, I know it lies somewhere here before the mean, with this area simply being 4%, which is 0.04. Got it? So what I can simply do is, I know if this is 0.04, 1 minus 0.04 is simply 0.96. I can go to the table here. I can simply calculate from 0.96. Okay? So if you see here, I have 1.7 for 0.9599. So I basically have 1.75 okay, with a 1 because this is 9 we need 6, so I do 1, so 1.751, but this will be minus 1.751 because it's less than, okay, and it's basically less than the mean. So now I compare my modulus of my z statistic value with my modulus of z, which basically means the modulus of my z statistic value, which is minus 2.182, with my modulus of minus 1.751, which is basically 2.182 with 1.751, and I know this will be larger. That means I can simply say that I reject my null hypothesis, and there's evidence of the height being evidence of height decrease, okay, at 4% significance level. Okay, so basically if you think about this graphically, minus 2.182 I know will lie somewhere, correct, which lies in the critical region because it's lying in the shaded area. So you can think about it like that also. Okay, now explain why it was necessary to use the central limit theorem in carrying out the test. So you use the central limit theorem only when they haven't specified the population distribution, and if they haven't specified whether the distribution is normal or no. So you can just write population distribution, okay, unknown, or normal distribution not specified. Okay, this is what you can write, because you use the central limit theorem only when they haven't specified the distribution. So if n is more than 30, we can approximate it to normal distribution. So yeah.